over p, you have both positive and negative p, and the complex conjugate is just the negative p, so you average both when you integrate, and it's real. F is real. But F is relativistically invariant, and if it was real for the 2 times equal in another system, the 2 times are equal somewhere else, and so forth, and therefore, since it's relativistically invariant, it must be real for any T2 and T1 which are space-like separated. Fun. Now, since it's real for any T2 and T1 space-like separated, it's equal to its complex conjugate if T2 and T1 is space-like separated. And therefore, one solution is that G is the complex conjugate of F that has the right sign on the frequencies and that's equal to F in the space-like region. And that's a unique solution, because if I had 2 of them and subtracted them, the difference would be 0 over a finite interval. And I said there's no solution to something with one sign of energy and a difference 0 over a finite interval. So this is extrapolatable out into the times T2 less than T1 in the past light cone, and this is our answer for the amplitude in the past light cone. So here's the answer for the whole amplitude for everywhere. If T2 is above T1 in the forward light cone, it has to be this expression. In the intermediate, where T2 is outside the light cone of T1, it's either this one or that one. They're equal. And for T2 earlier than T1 in the back light cone, this is the right formula. We started by supposing something was relativistically invariant, and are able to deduce what happens when you go all the way around back on the other side. And that's not so mysterious. Suppose we had 4-dimensional Euclidean geometry. X, Y, Z, and W, all equivalent, so the sum of the squares of all those 4 things was constant. And we start to discuss rotations in that space. That's the analog of relativistic transformations in 4 space, okay? I can invert X, Y, Z, and W by a rotation. Because, for instance, I can rotate in the XY plane and change X to minus X and Y to minus Y. Another allowable operation is to rotate in the ZW plane and change Z to minus Z and W to minus W, see? 4-dimensional. So you can change all of them around. And therefore, once you've supposed the thing is invariant, you know where it is everywhere, even upside down. The only difference in the Minkowski space is that there's a kind of a no man's land where T2 and T1 are outside the light cone, and all the transformations can't really move you through there. But we have obtained the correct continuation because the continuity is maintained by supposing that the energies are always positive. That limits the solution. In other words, this operation PT, which changes the sign of everything, is really a relativistic transformation. I should say more correctly, a Lorentz or rotation transformation, kind of. Extended across the mysterious space-like region by the demand that the energy is greater than 0. So it's not mysterious that we can work out the whole function. And it's not mysterious that relativistic invariance produces the whole works. Okay? So that was all right for spin 0. And now I'd like to do spin 1/2 and see what happens. There's a way of representing, once you start knowing that the thing is spin 1/2 and you have Lorentz transformations, you can work out by nice arguments about group theory exactly how all the states change and everything else. Without inventing the gamma matrices. Of course, you end up finding them, but it's all a group theoretic business, which I won't go into. It's a lovely exercise. But let's start out, and I'll give you some results of it rather easily. Anyway, first we just deal with ordinary rotations, and we know that if a thing has an angular momentum m along the z-axis and you rotate around the z-axis, the phase changes by the I m phi, and when it's spin 1/2, m is plus or minus 1/2, let's say plus, then it would be e to the I over 2 phi, and therefore a 360-degree rotation ends up by multiplying the function by -1. At this point, all attempts to do anything by instinct, by intuition, fail, of course, because it's hard to understand that, you know. I mean, one of the things that's the hardest part of this is to keep track of when you should have the -1 and when you shouldn't have the -1. Dirac had a very nice demonstration of this fact that rotation one time around can be distinguished from rotation. When rotation twice around is about the same as doing nothing. And I'll show you something you can find in Dancing Girls Do. Here I'm going to rotate. Remember which way. Around, all the way around until you can see the blue mark again. And I rotate it 360 degrees, but I'm in trouble. I can't undo. But if I continue to rotate it still further, which is a nervy thing to do under that, I do not break my arm, I straighten everything out. And so 2 rotations is equivalent to doing nothing. But 1 rotation can be different. So you have to keep track of whether you've made a rotation or not. And the rest of this talk is a nerve-wracking attempt to try to keep track of whether you've made a rotation or not. I mentioned something else I'm going to need for shortcut to give you an idea of the nature of the formulas. If you want to, it's typical in this thing to have half-angle formulas. For example, the projection, if you would like to know with what amplitude, if it's up in the direction z, with what amplitude is it up in the direction z prime, which is at an angle theta, to z, the answer is cosine theta over 2, which is the square root of 1 plus cosine theta within a factor. Now we're going to do the same thing, adding relativity and going through this group theoretic analysis, which is I'm not going to do. I'm going to use a scalar coupling. I have a constant e squared minus p squared equal m squared as a constant, and that's like cosh squared minus sinh squared, instead of cosine squared plus sine squared. So in this relativity, you have coshes and sinches where you would have cosines and sines. In the other theory, and the energy would be m cosh and the momentum m sinh of w. Now it turns out that these, no, this should have been a w, right? Yeah. I can say it, and you don't have to actually do it. That the amplitude, for instance, if you started with spin up here and you asked with what amplitude you go into the correct a spin state in the direction p2, starting from rest at p1. p1 is m, the time component, and no momentum. p2 is e, the time component. Let's say it's moving in a z direction. The amplitude that you get is typical of the amplitudes for a half-angle spin, except they use half the w, or rapidity, and the answer is to this problem is cosh w over 2, which is within factors which I'm not going to keep, like 2's and m's and things, is the cosh of v plus 1 square root. The amplitude to do that is this, and the cosh is really e, so this is the square root of e plus m. If you like it in a more relativistic form, consider p1 dot p2 plus m squared. By the dot product of 2 vectors, 4 vectors, I mean the product of the times minus the space components. And if you multiply the times, you get me, and all the spaces give 0. So p1 dot p2 is me. And here's a nice relativistically invariant looking expression. I mean, it's an expression for this amplitude in terms of p1 and p2. Now here's the thing that I wanted to say that we hadn't said before, but it's another important thing. I talked about turning everything over. But it's also possible to imagine that one of these vectors is turned over to be the opposite direction, and then we'd have a positron going into an electron. We have pair production. And we can calculate the amplitude for pair production by a continuous transformation of the formula that we have in terms of P1 and P2 until one of the p's is backwards. For example, if one of the p's is the positron, it would be coming in the other way, and if the positron had any momentum p and energy minus e, then the p2 vector that we represent it by, because we're drawing it upside down or backwards, is minus e minus p. Well, p1 is the same old thing, m. So p1 dot p2 is minus me. And it turns out that the amplitude for pair production, sure enough, is obtained by just substituting this value for p1 dot p2 in here. And by doing a little arithmetic within a sign, it's I times the square root of E minus M. And therefore, the probability of getting a pair is E minus M times some units, which are analogous to the scattering amplitudes. And this is a very interesting thing because it shows you how pair production rates can be calculated in terms of scattering rates by just shifting the vectors about. And of course, this is greater than 0. That's absolute square of that. Now, when we go and look at our pair case, where this was green last time, but I haven't got a green pencil, so it goes here, it goes this way, that's the one term, and then the other term goes backwards, and we tried to connect them last time by a kind of continuity. This time, because of this, if we went to the same state again, we get the square root of E plus M twice, and we get E plus M here. Well, how will it continue over here? Do you remember, if I didn't have the E in either place, that these two functions are the same in the space-like region? If they're the same, their derivatives are the same. So what fits together is the derivatives. If you take the derivative, let's say with respect to T1, or T2, for instance, that would produce an E. And this, in the same place, would produce a minus E. That is the signs, hey. Well, that's wrong, okay? This one is backwards. This is T2 minus T1. Right. And the derivatives have opposite E. So this continues into that. Now what happens? I can't move. You see, everything is forced on me, all right? No tricks. Now we go to look at the real part of this one, and it does the same thing as it did in the case of the boson, and it produces the right rate, which is the square of this, which is E plus M. But then when I look at the real part of this one, it doesn't produce the right rate. It produces the rate minus E plus M instead of E minus M. It's the opposite. It's the reverse sign of the Bose case. Therefore, the real part of this number 2 diagram this time is no longer the negative of the probability of producing a pair. It's the positive of it. It's a reverse sign. I mean relative to the Bose case. Now, you remember what we had to have for the Bose case? That because this thing was coming up very strong negative, we had to increase the probability when there was a particle present. Now it's coming up with the wrong sign. That means we have to decrease the probability when there's a particle present. And this indicates why it is that the thing works. It all fits together only if you say that when there's a particle in state 1, the probability of producing another particle in state 1 by a pair production is decreased. Instead of going up to 1 plus 1 equals 2, as in the Bose case, it goes up to 1 minus 1 equals 0. In the Fermi case, and the rule is that they have a particle in a state, you can't make another particle in that state by a pair production. And the fact that that particle is preventing something that you expect it to happen from happening shifts the probability the other way, and it fits with the fact that the sign is reversed. And so you see, at this level, we have a completely clear clue that we are going to be able to demonstrate, in fact, we have for specific examples, the connection between spin and statistics, and that is different for spin 1/2 than it is for spin 0. In fact, what happens is, it turns out, I mean, it's rather interesting. It's very curious that you can make any functions that match in that region. It was the luck that we were able to do it. If you take more complicated functions, they won't match. That is, the positive frequencies can't be matched exactly with the negative frequency, because the positive frequency piece has two components, the real and the imaginary, and the negative frequency one will have to fit both, which is too much. So it's just luck that it worked. The only thing that will continue to work is if the functions are matched, their derivatives match and higher derivatives match. So the only thing you can put in here are polynomials in the numerator. And that's one of the reasons that for years people have been stuck with quantum field theory, in which all the couplings and all the propagations involve gradients, and more gradients, but never non-local couplings, because they just drive them nutty because they can't make this thing fit. So that we learned something else in there. while we were at it. Okay? And, the first thing that happens, you see, the scalar case is just a constant. Then if it's linear in the momenta, that means the square root of momentum on each side. Spin a half is sort of splitting the linear thing. If it's quadratic, that's a spin one object going across, and so on. And it alternates like that. And depending on whether it's an odd number of powers or an even number of powers, this sign gives me